In this lesson, we'll continue our discussion on big idea number 1. What are equilibria and how can they quantitatively be described? And we'll tackle learning target number 3. By the end of the lesson, you should be able to determine the equilibrium constant, or Kc, of a system and explain its significance. You should also be able to use an accepted Kc value to calculate chemical concentrations at equilibrium. Depending on the thermodynamic favorability of the forward and the reverse reactions, the proportion of reactants and products in a system at equilibrium can vary. If the forward reaction is more spontaneous, then more products will exist in the system than reactants. If reverse, then the amount of reactants will be higher. The reaction which is more favorable can be determined using the law of equilibrium developed by Goldberg and Wage. They discovered that even if you start with different concentrations, there is a constant ratio between the equilibrium concentrations of reactants and products for each particular reaction. This ratio is known as an equilibrium constant, and it provides an easier way to quantitatively measure the thermodynamic favorability of the forward and reverse reactions than plugging actual numbers into the Gibbs free energy equation. The equilibrium constant is dependent on temperature, so reaction conditions are usually attached to these values, but they are not involved in the calculations. Below is an example of how equilibrium constants were derived. Here, if I have the equilibrium, N2O4 produces 2 NO2s. The forward reaction would have a rate law of rate equals Kf, indicating the forward, times the concentration of N2O4 to the exponent 1. The reverse reaction has the rate law rate equals Kr times NO2 to the 2. By definition, at equilibrium, the forward and the reverse reactions happen simultaneously at the same speed. Therefore, their rate laws can be set equal to each other. Now we rearrange this equation so that the constants are on one side and the chemical concentrations are on the other. So I'm going to divide both sides by Kr, and I'm going to times both sides by the concentration of N2O4. Now, instead of referring to the equilibrium constant as Kf over Kr all the time, Goldberg and Wage simplified it to a capital K with a subscript Eq, which stands for the equilibrium constant. The equation used to calculate an equilibrium constant is called an equilibrium expression. Now let's have a closer look at this equation. Here, if we look at our equilibrium, this equation takes the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to its coefficient. That is the general way to set up an equilibrium expression. Now that you know this trick, you don't have to derive an equilibrium expression for every equilibrium you encounter. There are different kinds of equilibrium constants depending on the type of the reaction and what you use to calculate it. If the molar concentrations of all the chemicals at equilibrium are used, the equilibrium constant is called a Kc, C standing for concentration. Once the equilibrium constant is calculated, it is interpreted in the following way. If the K value is equal to 1, that means the system has equal amounts of products and reactants. The forward and reverse reactions, therefore, are equally favorable or equally spontaneous. If you have a K value that is greater than 1, it means that the system has more products than reactants. The forward reaction is more favorable than the reverse. This can also be described as the equilibrium position being to the right. The cutoff is if your K value is greater than 10 to the 10. This means that the system essentially contains only products and no reactants. We interpret that as the forward reaction going to completion and the reverse reaction rarely occurring. The equilibrium position is described as being far to the right. If your K value is less than 1, it means the system has more reactants than products, and the reverse reaction is more favorable than the forward. The equilibrium position is described as being to the left. And the cutoff is if your K value is less than 10 to the minus 10. The system essentially contains only reactants and no products. This means that the reverse reaction goes to completion and the forward reaction very rarely occurs. The equilibrium position is described as being far to the left. Let's have a look at some examples. For example 1, we have to write the equilibrium expression for hydrogen and oxygen producing water. If I'm using equilibrium concentrations, I'm going to write it as a Kc. I would take the concentration of the products, which is water, raised to its coefficient in the balanced chemical equation, and I would divide it by the concentration of the reactants, raised to their coefficients in the balanced chemical equation. I could then sub in molar concentrations for these three chemicals and find the value of Kc. Let's have a look at example 2. At equilibrium, a 2-liter jar contains 0.302 moles of N2, 0.196 moles of I2, and 0.673 moles of Ni3. Calculate the equilibrium constant for the reaction, and then interpret what that value means. Using my equation, I'm going to write the equilibrium expression. Kc will equal Ni3 squared, which would be the concentration of my products raised to its coefficient, divided by N2 to the 1 and I2 cubed. I can use the information in my question in order to find the molar concentrations of each of those chemicals. In order to do that, I need to use the grade 11 equation, concentration equals moles divided by volume. To find the concentration of Ni3, I would take its moles and divide it by 2. I have to do that for each chemical. the Kc value equals 797. Because my Kc constant is higher than 1, it means that I have more products than reactants in my system at equilibrium, and that the forward reaction is more favored than the reverse reaction. But by how much? K values can go as high as 10 to the 10. By being around 800, it means that the forward reaction is just a bit more favored than the reverse.